Welcome to this puzzle session. Here is the puzzle we are looking at. So we have n integers, n is some positive integer, and we have n some integers. They can be same, they can be different. There's no constraint, just a sequence of n integers is given. Then we want to show that some consecutive subsequence sums up to a number that is divisible by n. So let me explain this statement via an example. So consider this sequence. Suppose n equals 5 and consider 1, 2, 4, 2, 4, let's say. So these are our 5 numbers. This is A1, A2, A3, A4 and A5. So, okay, so what are the subsequences? Consecutive subsequences. So by that I mean things like these 3 numbers or these 2 numbers or just a single number. Any bunch of numbers that come one after the other. And what are the subsequential sums? If we just focus on consecutive subsequences, what are the sums? So if I just take the single number, I get a 1. If I take these 2, I get a 2. Let me not use blue, let me use some other color. So if I take this one, then I get a 1. If I take these 2, then I get a 3 as a sum. The first 3 will give me 7. The first 4 give me 9. And all 5 will give us 13. What about the second 2, meaning 2 and 4? So that gives us 6. This is 8. And this is 12. Okay. This is 2. And this is, sorry, this is not 2. This is 6. And this is 10. So we see the sum of these 3 is actually divisible by 5 as the problem, this confirms to the problem that there is indeed a consecutive subsequence which is divisible by 5. So yeah, we didn't need to go further. We found the thing that the problem asks us to find. Anyway, so we need to prove this for general n, not just for n equals 5. Okay, so here is the main idea. So consider the numbers S1 up to Sn defined as S1 is A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3, and so on. Sn is the sum of all the things. So we have defined n other numbers. And if some Si is divisible by 5, sorry, not 5, by n, then we are done. Because each Si is a consecutive subsequence, the sum of some consecutive subsequence. Namely, Si is the sum of the first I of the AIs. Alright, so if this were the case, then we are done. So we may assume that none of the Si is divisible by n. So assume on the contrary, or rather assume, as how shall I say it? So we are assuming the unfavorable case. The favorable case is that some Si is divisible by n. So we need to deal with the unfavorable case, which is that none of the SIs is divisible by n. Okay, so what we'll do is we'll record the remainders of these SIs as we divide them by n. So let us list all these numbers in a row. Let me write one more, S3. So we'll just, below each SI, we'll just write its remainder that it leaves when we divide it by n, and that remainder could be, some R1 up to Rn. We don't know the values. Some R1, R2, R3 up to Rn. So note that remainder, any Ri, therefore, let me use a different color. So any Ri is less than n and greater than or equal to 0. That's what remainders are. Right? So if any Ri were 0, then we were done, as we noted. If this were the case, then some Ri would be 0 and then we were done. But we are assuming the unfavorable case. We are assuming that none of the SIs is divisible by n, and therefore none of the Ri's are equal to 0. So in fact, we can write this is strictly, which is same as saying that this is the case, which is same as saying that this is the case. So basically, these Ri's take values from a set of size n minus 1. Each Ri belongs to this set. So these are n pigeons which have to be placed in n minus 1 cages. So you can follow the video flashing on the top right corner of the screen, and it will take you to a quick primer of the pigeonhole principle. But again, pigeonhole principle is just common sense. So if you have n numbers, but which take the value in a range of size only n minus 1, then two of the numbers must be same. So therefore, by pigeonhole principle, we must have that Ri equals Rj for some I not equal to j. So there must exist two different indices for which the values, the corresponding Ri's are the same. So let's say Ri equals Rj for some distinct I and j, and also assume that j is greater than I. So because either I greater than j or j greater than I, it's not very different. So let's say j is greater than I. So then we consider then Rj minus Ri is divisible, or I don't want to write this actually. What I want to write is Sj minus Si is divisible by n. Why? Because Sj and Si leave the same remainder when you divide them by n, so their difference leaves the remainder of 0. You can verify that. Basically, you can write Sj as nq plus some number r, and Si as nq prime plus some number r, where this r and that r are the same because they leave the same remainder when divided by n. So if you take the difference of these two numbers, you'll get something which looks like that. And this is of course divisible by n. So anyway, just convince yourself that this is divisible by n. But the main point is that this is actually a sum of a consecutive subsequence. What is this? This is equal to ai plus 1 plus ai plus 2 plus ... aj. That's what that guy is. So we have indeed found a consecutive subsequence whose sum is divisible by n, and that's it. That's the end of the problem. So a very nice puzzle, but of course not very complicated. The solution is not very complicated, but very elegant. Alright, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening. Now, see you next time.